Chapter 10, slides 22 to 26. Like the alkene chapter, we can also get rid of pi bonds and saturate them with hydrogens as if they were never there to begin with. Luckily for you, the mechanism is the same, so not to worry, we're still going to apply a Syn4 mechanism. We can use an array of metal catalysts to do this, just like we saw in alkenes as well. I'm not too concerned that you've memorized some metal catalysts that go along, but understand that we're in the same position. You know, we can't react the hydrogen gas very easily. There's no dipole there. What's the reason for it to want to break? There's really not a very polar system that we're working with, right? The alkyne doesn't have much polarity to it. So again, we have to consider the use of these metal catalysts to lower the activation barrier and make these reactions actually happen. The hydrogen, again, will adsorb to the surface of the metal, just like we saw. Let's say it adsorbs to the palladium surface. Okay, then we're going to apply a Syn4. Now remember, we've got the metal is literally a solid metal, and to its surface, the hydrogen adsorbs. So we've shown you this before. So the black is your metal catalyst. So this is your typical mechanism. Syn4 places the hydrogen and the palladium across the pi system in a syn-concerted fashion. Right? The pi bond acts as our nucleophile, making a bond with the palladium, making a bond with the hydrogen. And then because the palladium has lots of hydrogen adsorbed to it, it swaps out. It can reductively eliminate, giving us our final syn product. But how do you stop this train? You can't. I have an alkene now, and I know that these are the same conditions that alkenes were susceptible to for hydrogenation. So you just can't stop the reaction. You can't say, hey, stop after one addition. You can't whisper to your flask that you just want it to go once. You have really no control over this. It's going to do it again. Syn4. And the palladium exchanges reductively. And at the end of the day, we have saturated our 4-carbon system. 1, 2, 3, 4. 1, 2, 3, 4. We have no more pi bonds. We've replaced them all with hydrogens. Okay, so we went all the way from an alkyne to an alkane, as if that alkyne never existed. It's like we erased it. Okay, is it possible, though, to do one addition and stop at the alkene? The answer is yes, but we have to change our reaction reagents, right? We have to change the conditions. We can stop after one syn addition, so we're going to do Syn4 again, okay? And the only difference here is that we're going to use a very special catalyst. This was developed by a scientist named Lindlar, and the Lindlar catalyst ultimately poisons the palladium and it stops it from doing that second addition. So in the presence of an alkene, only the alkynes in your system will get hydrogenated. It is poisoning the palladium either through the addition of lead or barium sulfate and quinoline. Okay, so I'm not again, concerned that you know how the palladium is poisoned, just that it is, and it ultimately stops the reaction from happening on your alkene. So with this very special catalyst, mechanistically, nothing has changed. If I have a 4-carbon system, I have the palladium. I'm just going to put a little star next to it saying that it's poisoned and that this system is only going to occur once through a Syn4 addition. Nothing really new other than the fact that we used some crazy special catalyst which ultimately gives me my alkene. So I was able to stop at the alkene here using a special catalyst. That's cool. I'm greedy. I'm a greedy chemist. That's all good. You know, I made a, oops, Z are on Z same side. I made a Z alkene. What if I wanted the E alkene? What if I wanted the trans? I mean, this is cool. I'm able to control the reduction such that I get the cis double bond. That's really cool. And that's all governed by the fact that I'm using a Syn4 mechanism. I'm delivering both hydrogens from the same side. Is it possible to get the E? Yes. Can I use a Syn4 mechanism? No. I have to change my reagents if I want to facilitate the product being trans. Here's our next flashcard. How can I do that? Well, starting from my alkyne, I introduce at very low temperature either sodium metal or lithium metal in combination with NH3, ammonia, liquid ammonia. So what I want you to pay strict attention to here, because when you're doing this stuff, it can, I don't know, I think it can be a little confusing. Remember way back when we first started, I'm just going to make a little pay attention symbol down here. We've seen NaNH2. Okay, this is a great strong base. The Na is plus, the NH2 is minus, because the nitrogen has only 2 bonds and 2 lone pairs, and it's an ionic salt acting as a strong base. This is not to be confused with NaNH3. Okay, NaNH3 is 2 separate reagents, right? Na is that sodium metal. This is your sodium from the periodic table. It's a soft silver metal that you can slice and, you know, in high school, throw it in water and watch it explode, right? You guys are familiar with the sodium metal. Very reactive stuff, but we're talking elemental sodium, not sodium plus like NaCl, like you would find in salt where it's already given up its electron. Very, very different scenario here, okay? This sodium has a 1 valence electron, while Na plus doesn't have, it has a full octet in its valence electron shell. So very, very, very different. NH3 is a happy neutral molecule, and it's a liquid. It's ammonia. It's what you'd find under your sink, right? So just pay attention. I get a lot of students who look very quickly and they get confused between these two very different scenarios. We used NaNH2 to deprotonate terminal alkynes as a strong base. We're going to use NaNH3 as a system to do 1 electron transfer, ultimately getting us to a trans double bond. Whoa, how is this going to happen? Well, I write it down as a 1 electron transfer. We're dumping in sodium metal. This is elemental sodium. It's got 1 valence electron. It is looking so hard in the solution to offload this 1 electron to something that'll take it. I mean, please take it. But there's no chlorine around in the system, right? So actually, it's looking to the alkyne. Alkynes can actually do this. So the alkyne will accept. So remember, we've got 2 carbons here. One of the carbons will accept this 1 electron. Now, this is not a radical reaction where they're coming to form a bond. This is an ionic give and take scenario. Okay, go back and look at our when I talk about radical chemistry, radicals are coming together. Two arrows are pointing towards each other to make a bond, or they're going away from each other, right? That's not what's happening here. This is classic Gen Chem. I have elemental sodium looking to donate, shove off, not make a bond, but actually shove off a radical, one electron in its valence shell. Well, in order for the carbon to accept this one electron, it has to break one of its pi bonds. So I'm going to move one of the pi bonds over into the carbon next door, just to make room. What this does is now I only have 2 bonds between the carbons, okay? And I now have an orbital with a lone pair in it. That makes the carbon negative, right? This carbon is now negative. And the carbon that gained the radical is over on the right. So I have one p orbital that has a lone pair and the other p orbital has the radical. Now this is in equilibrium with the other geometry. But you'll notice that of these two, they're in equilibrium. The CH3s both being on the same side is not a good scenario due to steric hindrance. And the reason why we can actually go between the cis and the trans in this case is because the carbon-carbon double bond system doesn't have the typical substituents. It has an empty orbital or a filled orbital. Remember nitrogen, how we talked about nitrogen not being a stereocenter because it can equilibrate that lone pair. It tunnels and you can get this flip. Well, as long as you have an orbital that is not a bond, you can get orbital flipping. So what's happening is that these orbitals are flipping such that they're trying to find the lowest energy scenario. So once this occurs, once the sodium donates its electron to the carbon and the carbon shifts its pi electrons into the next door carbon, you've created these 2 open orbitals, which allows it to find the preferred trans geometry to avoid steric hindrance. And then what ensues is simply protonation, acid-base chemistry. The NH3, which is a very unlikely acid, serves to be the acid in this case. The negative carbon grabs the proton from the nitrogen, and voila, we have one of the hydrogens on our carbon now. What is the byproduct? Well, the byproduct, what's floating around? NH2 minus is floating around, and the Na plus, because the sodium gave up its electrons. So I've just created a very strong base. I'm working under very basic conditions. All we're going to do is repeat this. Another equivalent of sodium in solution donates its electron to the one that's already there, making a lone pair, so a proper anion. So now this carbon is negative, and another equivalent of NH3 acts as my acid, acid-base chemistry. The carbon protonates, and we end up with a carbon-carbon bond with a trans orientation of the system. It's totally governed by this ability to find, with those orbitals being open and electron tunneling occurring, those methyls will put themselves as far away from each other as possible to avoid steric hindrance. So we had to, pursue a different alternative mechanism so that we could favor the trans double bond. Now we don't get this going any further due to the reactivity of if the sodium is going to donate another electron, you'd have to put that negative charge into an sp3 system. And we all know that a negative charge carbon on an sp2 is much better, right? Because REO tells me so. You're constantly making a negative charged carbon here, and you made a negative charged carbon here. But in both cases, REO tells me that the more hybridized, right? So sp2 is better than sp3. There's more S character. So it gets to a point where the energy is just not viable. You can't have an alkene accept the sodium in a typical alkene accepting the sodium electron, because the negative charge at the typical sp3 carbon would just not be very stable. And so there's a limit to doing this. But that's a good thing for us, because this allows us to make trans alkenes through this process. All right, that's 3 hydrogenations under your belt. You can go all the way. You can stop at the cis double bond, or you can stop at the trans double bond. You guys have choices now, all with an alkyne. There's only one more reaction to cover, and it too is very familiar to you, ozonolysis. Now this one is complex. It's a tough mechanism. I'm not going to show you the whole thing, but I will show you a shortcut. I just want you to understand that the premise of how this works is the same as what we saw for alkenes. It's going to undergo a syn-4, or a mnemonic for syn-4. Here are the 2 atoms adding across the alkyne. You can use your pi bond as the first nucleophile, kicking the electrons in and making our new bonds. Syn-4. So you end up with these ozonides, which are explosive and extremely unstable due to those oxygen-oxygen-oxygen bonds all vying for that covalent electron system between them. Not stable at all. It does decompose, just like it decomposed for us in the previous case, right? Where we had electrons come in, pi bond breaks. The only difference is that we have a double bond here, and so you're not going to break it into 2 different systems. It's actually one system. And so this is going to rearrange into, and this is the part that you just don't have to worry about, it's going to rearrange into this anhydride. And because we're in the presence of water, the water will actually add to these systems in a way that we will see in Orgo 2, ultimately giving us two carboxylic acids. Oh, well, what am I responsible for? Well, I want you to know the syn-4 mechanism. It shows how you can get those 2 oxygens into motion. How do I do this, though? How do I figure out what the answers are? Well, you know me, I've got that little shortcut we can use, but we got to do a little bit more than just the shortcut. So here's my shortcut for you guys. You're still going to put on your karate chop gloves and cleave those bonds. This is how I would do it. And so I have a carbon, triple bond, right? So this is carbon 1, carbon 2, carbon 3, carbon 4. So carbon 1 and carbon 2. And I broke it, carbon 3 and carbon 4. And I'm going to put my caps on because I want to stop the bleeding. But Notice what happens when you put your caps on. The oxygen has 3 bonds and it's positively charged. That's not good. So what you're going to do is you're going to react it with water. You're going to attack the carbon and kick the electrons up and make it happy. Do it on both. And what you'll find is that you'll get carbon 1 double bond from the 2 to the oxygen with an OH2. And again, you'll get carbon 3 double bonded to the oxygen, also bonded to 4 with an OH2. And that's okay because after workup, you end up with the products. So right down here below is my quick and dirty way to sort of, I don't know, cut through the long rearrangement and circumvent the anhydride hydrolyzing with water to the carboxylic acid products. My shortcut does very similar to what we did in the alkenes, right? Karate chop them, pull them apart, cap them with oxygens. The only difference here is that the oxygens have 3 bonds and you can't end it there. Hence, you need to have the water come in and push those electrons up to satisfy the oxygen. Give it a try. It'll take a little practice, but I'm sure you guys can do it. Here's some practice for you.